Okay, let's start our second presentation. And Gregor recently joined IBM to lead their strategy for applying AI to digital automation. This will be his first time when he presents at DecisionCAMP, but he already sets a record by presenting twice, today and the last day. And his first presentation is about applying machine learning to data-driven decision management. I think it's quite interesting, especially to get this idea from one of the major vendors around. Gregor, looking forward to your presentation.
Thank you very much, Jacob. And thank you, Jacob and Sandy and others for organizing and for inviting me. I've actually been with IBM a little bit longer. The work on machine learning for decision management or decision intelligence is a little bit newer though. So my name is Gregor. I work at IBM based out of France, and what I'm presenting today is mostly based on research and projects between the product development team in the France lab and IBM research teams in Paris and Dublin and Zurich. We're all working around this topic of transparent machine learning, but also rule induction or scorecard learning as part of that. So this is what I will be talking about today. In general, here's the agenda. I'll just give an introduction to why and how of why we need transparent machine learning. I'll talk a bit about different model types at a conceptual level and some algorithms. I'm not going to go deep on this, but I want to convey some principles of some of the model types and some pros and cons of each one of them. So that's why I'm giving you a little bit of overview on things like linear regression, scorecards, decision trees, and rule sets, and things like that. Then I'll talk a bit about how we can integrate these transparent machine learning models into our decision modeling and combining predictions with prescriptive policies and so forth. So that's that. Why transparent machine learning? What's happened over the last 5-10 years is that increasingly we're applying AI to high stakes decisions. So this could be in lending and mortgage and other financial institutions and processes. It could be for recruitment, promotions, careers in companies. It can be admission to educational or other institutions where candidates are ranked and scored using various types of machine learning models, as well as in the legal systems where probations and sentencings can be informed based on risk associated to various individuals. So these are obviously high-stake decisions. The impact to the individual can be quite high. So increasingly, the organizations and the companies and the institutions making these decisions wants to make them in a very informed and credible and trustworthy way. We can see this also in terms of regulations. The most prominent one right now is probably the proposed European Union AI Act, which takes a risk-based approach. So it basically scores an application based on the perceived risk of that. And loosely speaking, I think for most business automation applications, we will probably end up in a limited risk or even a high risk. And in the latter, you need to do some kind of conformity assessments and certifications of how AI is used in these applications. And this then leads to requirements around transparency, providing detailed documentations for how decisions are made, as well as explanations of sorts, meaning ensuring traceability of outcomes and results. I believe actually the next talk is on the EU AI Act, so I'm actually going to leave most of those details happily to the next speaker. But this is one of the reasons. Regulation in general is one of the reasons. But in general, I think as organizations, as businesses, we actually want to make these high stakes decisions based in a trustworthy way because of our relationship with clients and our brand image and many, many other reasons. So roughly speaking, there's kind of two big trends within trust and compliance, if you will, for decisions. One is decision explainability. So once we made a decision, including an ML prediction, for example, We want to be able to not just make the prediction, but also explain that prediction. So this is what I would refer to as explainability. And as Jacob just mentioned, I'm actually going to cover that a bit on Wednesday, I believe it is, at 11. So please tune in then for a bit more of a deep dive on that particular topic. Because today I'm going to talk about the other alternative, which is more around model transparency, understanding how predictions and decisions are made in general, not just for a specific prediction or decision. So that's the topic of today. As you probably all know, business rules and machine learning are complementary. Across use cases and industries, we see increasingly how machine learning can provide us with predictions, assessments of the likelihood or propensity of something. So in a product recommendation setting, we often try to estimate how likely it is that a customer will buy a certain product. In underwriting, we might estimate the propensity of an existing customer to churn, similar in telco, the likelihood of a payment transaction being fraudulent, and so forth. So these are all kind of typical assessments or predictions we want to have. And using machine learning is natural for that. And also combining it, of course, with business rules, which is the action part of this. Based on policies as well as the predictions, we might decide what personal offer to give to a client, or determining whether we should inspect the fraudulent insurance claim or not, for example. So there's a duality and a complementarity between these two technologies. We sometimes put it very simply like this, that we use predictive models plus prescriptive rules to make a decision. So that's a simple kind of complementarity. What I think is happening now slowly, using predictions or predictive analytics is not necessarily new, but I think the use of this is increasing. So if you look at how decisions have been made based on human authored rules or regulatory rules, I think we're seeing that the data driven, the ML models trained on data is kind of shifting and taking over some of the tasks that were done using human authored rules before. You could take, for example, classical mortgage scenario where you might 20, 30 years ago have had a table assessing risk of a mortgage application based on income and debt and loan ratios and so forth. Today we might instead have a more complex or more sophisticated machine learning model to do that. And that is basically the ML model is taking over a task or a prediction that was previously managed by hand. And with that patterns of predictions plus prescriptive rules, there are some nuances there, not to be exhaustive in any way, but one way we might want to use these predictions to make a decision is to compute something. So in this scenario, which I'll talk a bit more about later, we might use the churn risk of an existing customer plus a prediction about the lifetime value of that customer, if the customer stays a customer, and use those two numbers and some other rules to compute a budget. How much do we want to spend on retaining that customer? Another pattern might be using what we often refer to as threshold rules. So let's say you're inspecting a payment transactions and you want to decide whether to block or inspect or let that transaction pass without intervention. You then do a fraud assessment or fraud score, assessing the risk that this transaction is fraudulent. And if the risk is above 70%, say, you block it and inspect it. If it's between 40 and 60%, you might let it pass through, but you put it on a queue for post hoc sort of inspection. If it's below 40%, you let it pass. So 40 and 70%, those would be the thresholds, right, for taking a differing action. A third pattern might be, which we see in product recommendations and upsell, cross-sell, is to produce a list of product recommendations for a specific customer, and then use a machine learning propensity model to rank which one of these offers are most likely to have a beneficial outcome, and then we sort of sort and rank and select among those possibilities. So these are just 3 patterns of using predictions within decisions, not to be exhaustive. There are probably others as well, of course. One thing to note here is that very often we have classification models, meaning for churn, for example, for a customer, we know from historical data whether this customer churned or not. So that's a true and false value. So it's a classification model. But often we actually don't use the classification for a prediction. We actually use the confidence of that classification. So for a new customer, it might predict churn with a probability of 70%. We actually use the 70% with some threshold rules, for example, or to compute the budget like we have in the first case here. So instead of the actual true false, we actually use the nuance in between to make use of the prediction. And not all transparent machine learning models, or not all ML models in general, support or give reliable confidence scores. So this is one thing to keep in mind, right? When you are using ML models in the context of decisions. Why are we looking at transparent machine learning? Well, the key drivers are probably those. We want models that are readable, right? That means they are in some kind of format that a human can read. The second thing is, of course, they need to be understandable as well. Just being readable doesn't mean you can actually understand them. They might be too large, too complex, have too many interactions and things that are hard to understand. You can't really grasp it. But we want both readability and understandability. In some cases, we also want to be able to modify these models. Let's say it's a rule set and 2 rules out of 20 aren't rules we want to keep. We might just want to delete them if it has minimal sacrifice in terms of predictive accuracy, for example. And the third thing is we want to govern these transparent models as what I would say business artifact, just like decision tables and business rules and all the other things we have in our decision management system. That means we want to be able to version them and manage them in conjunction with the other assets and rules. So that's probably the key drivers. And this, in a combination, leads us to having more trust in how these predictions are done, right? As a side benefit, I would say, assuming we import these transparent models, be it a rule set or a decision tree or a scorecard, if we import those into our decision management system, that also naturally lends itself to support not just management of those artifacts, but also execution of those artifacts inside our rules engine, if you will, which typically leads to better performance, lower latency, higher throughput, but also simpler system management and error handling. You have no remote invocations over REST, for example, to make, like you typically would if you are invoking a black box machine learning model. So you have one runtime rather than 2 or more, which is a benefit. So next, I wanted to dig into some different model types and just recap. I think many of you knows this before, but kind of level set on the different types of models we typically would talk about as being transparent. But before I dig into this, I'm going to be using an example just to orient around, and it's going to be this telco customer retention example. So let me quickly introduce that one and show you a couple of data sets for this example. So the top decision we're trying to make here is to determine if and what retention offer to give to an existing customer. And there's roughly 2 parts of this decision model. The first thing is that on the right-hand side, we create a list of potential candidate offers with an associated cost. So this could be anything from give a 10% discount to send a survey, or propose this additional family offer, or whatever it might be, right? So some type of retention offer that will hopefully be perceived as positive to the client. It's actually not just the cost, it's also the propensity here, right? I don't have this in this model, but that would be a natural thing to have as well, right? How likely is it that this retention offer is accepted by the customer? On the left-hand side, we calculate a budget. Basically, how much do we want to spend on retaining this customer? And this in terms, we use 2 machine learning models to compute. The first, of course, is the customer lifetime value. How valuable is it to keep this customer? And secondly, of course, the customer churn. How likely is it that this customer will cancel their subscription if we do not retain them? So that's if we don't do anything, right, to retain the customer. So those are 2 models we're going to use to make this overall decision. Input data is classic tabular data. The observation we have, so every row here represents a historical customer, and the observation for churn is true or false. True if this customer ended up churning, meaning canceling their subscription, and false if they stayed as a customer. The rest of this table is just the data we're going to use to kind of train. We would use to train these models. I'm not going to use all the fields in these examples, so just let me point out a couple. Age of the customer, of course, is simple. Monthly usage is the number of monthly minutes this customer uses their subscription. Rate plan goes from 1 through 4, 1 being a cheaper monthly subscription and 4 being a more expensive one. So that's kind of the main variables I will use from this data. If you look at the data very roughly, and this is actually, I'm faking it a little bit to be able to make my points later on, but you can imagine we're looking at the data, we're projecting it just on 2 variables: usage, the monthly minutes, and age of the customer. What you can see then is that these are then the customers who ended up churning, represented by a red dot, and these are the customers that stayed customers, right? And you can see that we have kind of 2 large clusters here. Top left is a set of customers with high usage and relatively young of age. They were more likely to churn. We have many observations of churn in that area. In the bottom, low usage customers, we have also a band of customers that were very likely to churn, or lots of observed customers that churned regardless of age. So this is the examples for churn I will use. I have a similar one for lifetime value. In this case, I'm looking at 2 other variables. I'm looking at the long distance calls, how many minutes of long distance. And I'm looking at the rate plan. Remember, rate plan was 1, 2, 3, 4, 1 for a cheaper subscription and 4 for the most expensive subscription. And here we're looking at deep, these are observations again, rows. Each dot here represents a row in the table. Dark green are very high LTV, lighter green, less high value, etc., down to orange, which is a low lifetime value, so less profitable customers. Okay. So first, just a very, very classic linear models. They've been around for over 100 years. And as a recap, the structure of a linear model is a linear combination of the variables times the coefficient. So you have the prediction is y is basically just a sum of a set of terms. The first term C0 is it's also often referred to as the intercept. It's just a number and baseline. And then you have C1 through Cn, which are the coefficients in front of all our variables. So it's a linear expression, it's additive, and training a linear model is just fitting this model to your observations, doing a regression. Often we talk about the least squares method, which means we're trying to minimize the distance between the observations and the predictions for that observations squared. We're minimizing the sum of those squares. And the reason we use squares is because we want to eliminate minimize the effect of outliers. So this works really well for numerical variables like age and income and so forth. For categorical variables, which we sometimes refer to as enumeration and on the DM space, like rate plan, we need to do a binary encoding, which means that we need to kind of, for all the possible values of this enumeration, we need to have a variable in our machine learning model. So if we look at what this one might look like for estimating the lifetime value, we would, and I'm simplifying a little bit here for those of you who are deep in machine learning, I'm simplifying a bit and you will recognize that. But conceptually, what we're doing, we're expressing the lifetime value as a linear combination of C0 plus C times the long distance plus CK times the rate plan. So it looks, as an example, looks roughly like that. We're training this model and the coefficient might be 0.1 times the long distance. So we are, and I'm overlaying that with a shaded here, right? So the contribution to lifetime value from the long distance variable is 0.1 times the number of long distance minutes per month. So that's 0.1. So for 50, that would be then 5, right? That's a contribution. For rate plan, we have to do binary encodings of this one. We have to look at each possible variable of the rate plan is either 1, and here we say that we might find, for example, that 10 times rate plan is a good coefficient for rate plan equals 1. For rate plans equals 2, it's 12 and 18 and 24. And again, I have used here darker colors to indicate a higher lifetime value, and yellow and orange ones to indicate lower lifetime value. So you can see on the right-hand side, we're kind of estimating the observations we have with this linear model. So this is kind of how linear models are used or trained. They are additive, as I said, which means that each variable contributes separately to the score. And that has a drawback, which is that if we have interactions with variable, if there's a statistical correlation between, let's say, age and income, for example, this is not something like the linear regression naturally is good at as predicting. We might get larger errors because of that. The typical way of handling it is to add new features, and I'll talk a bit about that later on, because this problem we have in other models as well. The second type of model I want to talk a bit about is ScoreCards. And ScoreCards are roughly in the same class of models as linear regression. A classical scorecard looks like this. So this would be an example from a mortgage application, typically. A scorecard has a set of, it looks at feature by feature, and for each feature variable, same thing, you have one row. The first row is age, and the second one is income, education, and whether this customer has a past defaulted on a loan in the past or not. For each variable, this is also called a characteristic in a scorecard terminology, we define a set of bins. And typically for a numerical variable, that would be a set of ranges. And for categorical variables, it would be a set or individual element. So for age, for example, let's say we are, in this case, we have a age of, so for each row, we're getting a subscore. So age gives us a subscore of 50, income gives us a subscore of 50 as well. The university education gives us 50, and no prior defaults gives us a score of 70, and then we add up all these subscores, and that gives us 170. So this is a very popular and classic model, historically authored very often by hand, to express or to do scoring in various industries, credit, insurance, also very popular in healthcare, for example, estimating your chance of a health problem in the future. So those are scorecards conceptually, one row per variable, and then there are bins for each variables, and the bins can be different, of course, for different variables. So let's look at how we would do the lifetime value with a scorecard. we're looking at the same long distance and rate plan on the right-hand side. And here we would then perhaps do 3 bins for long distance. So we won't just, with linear regression, we had a coefficient. Here we are doing bins. So if a customer is having less than 40 long distance minutes, that would give a subscore of 2. Between 40 and 50, we get a subscore of 7. Between 50 and 100, we get a subscore of 10. So again, I overlay that with darker colors on the right-hand side. For rate plan, similarly, we would have different subscores based on the rate plan of this customer. And overlaying this on the right, you can see that there are darker shades towards the upper right. For example, if a new customer, we want to predict the lifetime value for, if this customer, for example, falls in the second bin for long distance minutes, and the second bin also for the rate plan, we would have a 7 plus 12 being 19 as a total score. Differently, if a customer would fall in the third bin and the fourth bin respectively, would sum up the subscores for a total of 35. As you can see here, it's kind of a lot of similarity. Again, it's an additive model, just like a linear regression. The main difference is the binning, of course, which allows us to do non-linear trends at a variable level. So for example, we can see here that the long distance it's not a linear, as the number of minutes go up, the lifetime value doesn't grow linearly, it has more of an exponential effect or non-linear effect. So that's, in this case, scorecards are better at modeling non-linear effects compared to regressions. Training these scorecards, of course, if you want to train them from data, implies you need to find the relevant variables, because you might not want to use a scorecard with all the variables. And number 2, you need to create the bins. What ranges do you want to have? And third, you want to find the subscores for each variable and each bin. So that's pretty much how you do training for scorecards. There are various methods by this, which I'm not going to go into, but that's essentially what you're trying to do. You're trying to estimate the bins and the subscores. The next model I want to talk about quickly is, of course, decision trees and tree models in general. The classic type of tree is a binary tree where you have nodes and you split based on the value of a single variable at the time. There's a close resemblance between how we train decision trees and how we evaluate them. This is all kind of divide and conquer. We can have splits on numerical variables, or we can have splits on categorical variables. And again, if we're looking at now the churn example, we have age on the x-axis and usage on the y-axis. The way we would predict churn using a decision tree could look something like this. At the top node, we split based on usage, and we say that if usage is less than 40, we are gonna estimate churn. And if usage is more than 40, we will look at the remaining dots and see how can we split these in a way that we isolate the red from the green. So this might be we find a segment of the decision space where we have mostly green dots, and we separate that apart, and we'd say this is not churn. And we continue like this, looking at the areas in a divide and conquer fashion repeatedly or recursively until we basically has covered the whole decision space into areas like this. So the decision tree is essentially just a binary tree like this, where each leaf node indicates churn or no churn. Good with decision trees, they can handle both non-linearities, they can handle variable interactions, and that happens implicitly, right? As you go up and down the tree, variables do interact with each other, right? You can estimate those effects. Accuracy can be great with decision trees, but they are prone to get large, and it's easy to overtrain them, which means you go into specific areas of the tree just excessively, and you get a very large tree. So there's many algorithms, variations for managing the complexity, bounding the size of the tree, and avoiding overtraining. So that's basic, but it's still a classic model that is very very useful. And there's also a natural relationship with rule sets, which I'll talk about next. Because the next class I want to talk about is, of course, rule models, right? We use rules a lot in decision management, so it's natural if we can express predictions using rules, because then we can handle them and manage them and execute them just like we would rules. Again, looking at an example of usage and age, we're trying to look at predicting churn using rule sets in this case. The rule sets are similar to decision trees, but we typically here looking at a method where we kind of break off sections of the space. So for example, if we have a rule that says if age is less than 25 and usage is greater than 100, we predict churn. Then we find another rule that covers another area of the decision space, again predicting churn, and a third area. So now we kind of covered all the areas with some errors, because some predictions, some of our observations are now wrongly classified, but that's par for the course for machine learning. We have 3 rules that all predict that churn is true, and then we have a default rule. So this is a classic rule set, a set of rules all predicting the same thing, and each rule here you can think of as a hypercube. So if n is the total number of variables, this will be in hypercube of m, where m is less than n, right? So, for example, the first rule is a 2-dimensional kind of hypercube in an n-dimensional space. So they kind of these cubes kind of cover the decision space in n dimensions. Some quick terminology: we often talk about a condition being a condition or a predicate, and then we assemble one or more conditions into a rule clause. So in this case, we have usage is more than 100, age is at most 25, and then we predict t. As I mentioned before, for a rule set, all the rules in that set predicts the same class. In this case, that churn equals true. And then we typically have a default rule, which is the opposite class prediction. So that's a little bit how rule sets work. There is a close sibling to rule set, which is decision lists, also known as rule lists. They're very, very similar, but they are blended, and I'll show you how that looks. So we might have a rule that says age is less than 48, usage is more than 130. Then we have a rule that says if age is greater than 48 and usage is greater than 40, then we predict false on the churn. And then we have a rule that predicts churn equals true, and then we have a default rule. So the thing with this is that we have a set of rules that are ordered. In the prior case with rule sets, they are unordered. It's just a set of rules. Here we have a list of rules. They have an order, and we can blend the prediction, right? So in the first rule, we predict churn equals true, and the second one false, and the third one true again, etc. So that's we can blend the predictions in a quite flexible way. So they can sometimes be more compact, especially if you're using multi-classification, not just two classes, two values. Just a side comment, there's a lot of ways of dividing a decision space and achieve a similar performance or a similar accuracy for a model. And this goes for rule sets and decision trees and as well, right? Sometimes this is referred to as a Rashomon effect. It's the notion that for a specific data set, there are many equivalent models, but different, which means that you can find many models that are equivalent or close to equivalent in accuracy, but they look different. So you can imagine, for example, you can find a rule set that has an accuracy of 90%, but there's another 50 rule sets with the same accuracy, but a different set of rules, essentially. So there's many ways, as you can see, of kind of mapping the decision space and coming up with your rule sets or your rule list. So that's also something to keep in mind when you're looking or learning these rule sets, that there are many equivalence ones. Quick comparison between rules and trees and lists, right? So to get a feeling for how they relate to each other. If we're looking at a rule set like this, which predicts churn or no churn in the leaf nodes, what we can do, of course, is that each leaf node represents a rule. So we can just extract rules from a decision tree by looking at the leaf nodes, and each leaf node gives us a rule. And this means, of course, that we can take all the churn nodes here and create a rule set from that, or all the no churn leaves and create a rule set from that. And this is actually how many of the original methods for rule learning were done, right? Starting with many algorithms for decision trees and extracting rules for that. So what would a decision list look like? Well, it would look probably something like this, right? So you would have a special structure, right, just going in one direction. The thing to note about decision list is that there are if, else if, else if, else if in structure, which means that the condition in each clause here typically gets shorter because it is the inverse of the prior paths you did not take. So the decision lists are simpler in that respect, right? That the actual clause in each else if can be shorter because it reflects the negative of all the choices not taken above. But it also means that if you're reading and understanding them, you need to keep in mind of the branches that weren't taken above, right? So there's a pro and cons in that case. Finally, on rule sets, you can express both rule sets and decision lists as decision tables, of course, each rule then being a row naturally. And in the action columns, you would have the class prediction, the confidence of that prediction, etc. And empty cells represents variables on which you have no predicate, no condition on. So that's kind of natural. The reason I'm saying this is because in some cases, a decision table is a much better representation, and in some cases worse. Typically, if you have a dense rule set, which means you have lots and lots of conditions on lots and lots of the rules, it is easier to represent as a decision table, meaning lots of these cells will be filled in with something. And that makes it easier for you to see interactions. You can sort and search and rank, these columns, and you can easier analyze the rule sets compared to having a set of if then else rules. A few things on algorithms. I mostly talked conceptually so far, but there's a couple of things on algorithms I'd like to highlight. Classical rule learning algorithms, once the rule learning went beyond just extracting rules from trees, but rather learning rules from scratch, many of them were based on what you can think of as heuristic search. And Ripper is one of the more prominent ones, invented in the mid-90s, and it's still kind of considered state-of-the-art, at least for accuracy of rule learning. It works something like this. You start with an empty rule and you add conditions to that rule to form a complete clause. And let's say that is rule number 1, expressed on usage and age in this case. So you remember that rule and you remove all observations from your data set that is covered by this rule. Then you repeat that and you find a second rule, again, that covers what you're looking for, in this case, churn. In this case, you can see we have a couple of misclassified observations, the 2 green dots, but that's something you'll have to live with. We remove those observations and we repeat again. Find a new rule until we're done, basically cover all the churn cases, all the churn observations that we wanted to cover. This tends to create, it's actually a little bit similar to decision trees, tends to create kind of large rule sets with high accuracy, prone to overtraining a little bit. So there's, in the Ripper algorithms and similar algorithms, there's typically a lot of kind of heuristics, ways of pruning and optimizing and simplifying the rule set, both iteratively as well as a post-processing optimization. So but this is a classic way of learning rules sort of from scratch. And these algorithms are usually called separate and cover. I mean, you're separating a part of the decision space, you're covering those observations, and you remove them and you iterate. So this is very classic. Limitations of these types of algorithms, and actually limitation of these rules that are made up out of boxes. If you have any kind of linear effect or interaction between variables, what often happens is that since all these boxes are orthogonal to the axis, age greater than 40, usage greater than 100, etc., what ends up happening is that you end up with many of these boxes to kind of estimate or align with something that is linear or non-linear in nature. So, and that's one of the reasons why you might end up with lots of rules to have a decent accuracy, and lots of rules is not good in terms of transparency because it's hard to understand, right? So that's just one general kind of problem with orthogonal problems. So you can suffer explosion in rules in presence of variable interactions or non-linearities. Solutions to that implies, number one, you have to add new variables, sometimes called feature engineering. You're adding new variables. In this case, a composite variable. You might divide age by usage. That gives you a new variable that you can use in your rules. You can also have rules that are where the clauses are not just orthogonal to the axis, but actually being more complex expressions, such as a linear equation, for example. But then you typically need a different way of learning these rule sets. I wanted to point out a couple of at least one other type of more recent method, because most of what I talked about so far for learning decision trees and rule sets are, well, they were invented probably more than 20 years ago. There are some recent innovations in rule learning, and I want to highlight one or two of those. One class of such methods is actually based on mathematical optimization. And it looks something like this. Instead of learning the rules incrementally, you consider a lot of potential rules as candidates. So initially, then you create a set of possible rules. For example, you can take rules that have a single variable. So age is, in this case, usage is less than 200 or greater than 180, greater than 140, greater than 100. So you create a lot of potential candidate rules just with one variable. You do the same with the age variable. And then you start create candidate rules involving two variables, age and usage. And then you go up in dimensions, creating these all the way up to kind of m-dimensional boxes in space. So this then means that you have a large number of potential rules, hundreds or thousands of them. And your problem then is to select a subset of these rules to form your rule set. And that is a classic optimization problem. It's kind of reminiscent of a set covering problem in the operations research literature. And there's two ways of doing this. So the Corels algorithm came out around 4 or 5 years ago. It uses a branch and bound method to create a decision list. So think of this as a search tree, where in each node you branch on a variable, and that search tree becomes your if then else decision list. And they use various heuristics to reduce the search space with upper and lower bounds and so forth. So that's Corels. It's one of the newer algorithms in this area. Another one comes from IBM called BRCG, Boolean Rule Column Generation. Similar premise, meaning that you are trying to solve this set covering problem, but you do it using a column generation approach. It essentially means you have two optimization problems. You have a master problem that does this set covering, and then you have a pricing problem that generates new columns, meaning new rules. So you don't create all of these rules up front. You generate some of them, you solve a set covering, and then you look at what types of rules are missing, and then you have another problem to create more of these rules. So it's kind of an incremental addition of candidate rules. The good thing with these approaches is that they can potentially, well, number one is if you let them run as long as they need, they will create a quote unquote optimal set of rules that is minimal in size, however you define size. In practice, though, you have time limits and so forth, but they can generate smaller and more compact rule sets compared to some of the others. Bonus is it's easier to put constraints on what types of rules you want to have and so forth. Finally, I want to make a little advertising for a session tomorrow. My colleague Christian will have a keynote tomorrow on neurosymbolic AI and decision rules. And he will then cover another way of learning rules, which is by representing them as neural networks, as topologies in a neural network. So please tune in for that tomorrow at noon. Quickly, just on all these types of models, I'm not going to go through these exhaustively. I just want to note that depending on your data set, depending on how you want to use your predictions, some models might be better than others, and some have some issues. For example, we talked about the model size growth. If you have only orthogonal boxes, that can be a problem for some of these transparent models. ScoreCards and linear models are additive, and they are not great for linear interactions between variables unless you add new variables. Trees and rule sets, you can use predict numbers for regression, but they're not naturally made for that. You might need more rules or larger decision trees to do that effectively. And finally, not all model types provide a statistically sound confidence prediction. So if you're really going to use the confidence of a prediction rather than the prediction itself, you want to pay attention to that. So very quickly, how do we kind of implement this? The traditional machine learning flow is still intact. We take historical data, we learn these models. We currently use PMML, predictive modeling markup language, as a way to transfer these transparent models into our decision management environment by importing them, whether it's a rule set or a scorecard. And just coming back to where we started, if you look at the way we modeled our decision, in this case, using the churn confidence to compute the budget, we have a node that computes the churn, which we also represent as a simple decision model. In this decision model, we do some data mapping because that might be the structure of the ML data can be different from the data we use on the decision modeling. So we do some rules to do the mapping. Then we have a main prediction node where all the rules are. So these are the rules that we imported from the rule learning algorithms using PMML. And then depending on the hit policy, the evaluation policy of this rule set, we might have some more nodes, right, to weigh and compare and determine the final classification. But basically, this is how we structure and how we embed the transparent models inside a overall decision model. Final thing I'll notice with this, we are, of course, all used to looking at governance from the business and IT perspective, and a lot of the part of the raison d'etre for decision management and BRMS initially was to separate the life cycle of rules from the life cycle of IT and releases. Now we have another life cycle to consider, which is the data science life cycle. So we need control over when we import rule sets and other transparent models, how we version them, when we retrain models, and how we replace and compare, right? So there's a governance and kind of simulation aspect to this, of course, because now we have another life cycle that we might not have had before. I think that's about it that I had. Just to recap, key drivers: readable, understandable, modifiable. Those are the key drivers for transparent machine learning. Bonus, faster execution, essentially. And that's it. If there are any questions, I will be happy to take those.
That's great, Gregor. Thanks very much. We actually have a number of questions in the Slack channel, so we're probably not going to have a chance to address them all. I'll just try and get to a couple of them, and then if you can pop over there later, you can look at the rest of them. Tom had a great question about just a general comment on some of the spectacular failures of machine learning. I think that's probably a much longer discussion. So maybe we leave that in Slack, or we have it during more of an open chat. But I'm just looking at Jan's question here about how you're using the machine language coefficients and results as input information in the decision model, but does that improve model transparency? And then what about neural nets or SVMs? Are they transparent even if you derive rules? So just, kind of looking at how much is this adding transparency?
Yeah, no, so a neural net, I wouldn't consider transparent. Neither would I consider a support vector machine as an SVM transparent. They are too complex for a human to understand. You can extract something transparent from them, maybe, right? And maybe, you can extract rules from a neural network. And I think you'll see that tomorrow if you join Christian's keynote. You can extract rules from non-transparent models, but by default, I would not consider those transparent. Linear models are also can be transparent, but it depends on the domain and it depends on the size of these linear models. So all of them, they're all different. They're all suitable for some things. They're complex in different ways, I would say. So it's all very specific to the use case.
Okay. And Alan had a question as well, just about the difference between transparency and explainability. And I think that might tie into the presentation that you have on Wednesday as well. Like he said, for example, large decision trees are transparent, but not really helpful as an explanation just because they're so complex to look at.
Yes. Yeah. So large decision trees or forests of trees can be great to use for predictions. And they are quite good to derive explanations from. If you're just making one prediction, they're quite good to get a confidence for, and they're quite good to get an explanation for, because you can look at, because you can go down to the leaf node of that decision or the prediction, and you can trace up and see why that prediction was taken. So they're good to justify which variables were involved in a prediction. They can say, well, this prediction was made because of your income, your age, and your score or whatever. They're not good for counterfactual predictions or explanations. And I'll talk a bit about that actually, I think on Wednesday. Counterfactual meaning, what could I have done to get a different outcome?
Right.
Right. You don't know what the boundaries are for getting a different outcome. So in that case, they are not always as great. They're all pros and cons for those.
Okay. There were a couple of questions just about the IBM products here. It's just like Jacob was asking, what's the actual % of ML plus rules cases inside all of your ODM customer cases? And Sylvie was asking, what's the customer feedback on these features, or is it still in the research stage? So just kind of getting an idea of what you're seeing in the marketplace.
Yeah. I put a couple of links here actually on this last summary page. So once you download the PDF, you can click on those. These are links to some articles about the products and a video if you want to see a demonstration of what it looks like in our automation decision services, which is the product where we put in most of the ML integration into to date. In terms of customers who use machine learning together with rules, I don't have any exact numbers. I know it's for sure more than 10%. It's probably less than 50%. I would estimate it's somewhere in that range. Exactly where it is, I don't know. And part of the reason we don't know is because there are various ways of integrating it. Traditionally, it has been very popular to do batch scoring. So every night or every week or every month, you score, for example, all your customers on risk. And then you just use those scores as data, right? So it's a very loose integration between machine learning and business rules. Doing predictions dynamically in real time is becoming more popular. And in some cases you have to, right? Because you can't pre-score everything, right? Of course, you can't pre-score a payment transaction because you don't know the transaction before it, pops up, right? So in some use cases, your only choice is to use it real time. But I think it's a minority of customers, but a growing minority, and some of the more interesting use cases and high value customers are in that segment.
Okay, that's all we're going to have time for now, because we're going to
Very
need a little bit of time to switch over. But there are some other questions and discussion points on the Slack channel if you can take a
I'll
look at
pick up on
there.
those. Yeah.
Okay,
Thanks so much, guys.
great. Thanks, Gregor.